Okay, it's time to start the session. Kotlin Backstage by Mitchell Tilbrook. So please go ahead, Mitchell.
Thank you. Okay. So today I'm going to be looking at a few things. So we're going to be looking at some bytecode. The bytecode's not really the point of the talk. We're just kind of going to use the bytecode as a way to kind of see what Kotlin's really doing behind the scenes and dig into how Kotlin is actually bringing some of these more modern language features to a runtime, which in a lot of cases doesn't actually support the type of semantics that we're actually using in the language. I'm going to have a few things where I'm going to talk about the consts and where you should be using them and how you should be using them and that you should be using them, as well as looking at things like how statics work in Kotlin, because we're used to in Java being able to declare statics pretty much anywhere, whereas Kotlin forces us to put them in very specific places, as well as the impact on scoping and method count and how we don't really have the same scoping rules in Kotlin, so how does that actually translate into bytecode? So the first thing is just to start with something simple. So it's going to have a look at the primitives. So in Kotlin, we don't really have the idea of a primitive and a class variant. But what happens is that if you have a primitive which can be nullable, Kotlin is always going to use the class variant of it, because you can't actually have a null variant of a primitive. Like the null case would probably for an integer just be 0, which is a value anyway. So we've got string interpolation. So the way in which Kotlin does this isn't too dissimilar to the way Java does it, but Kotlin will just do it way more efficiently. So we've just got a number, and we're going to interpolate it into the string that we want here. And what Kotlin does is it actually generates a string builder and then uses append at the point of where you put all the dollar signs. Now, if you're using Java and using just the string plus, this will still use string builders, but it'll make a new string builder for every plus operation. Whereas in Kotlin, it will use the single string builder for all the different variables that you're trying to interpolate into your string. Classes, so this is pretty simple. Kotlin allows us to be a lot more succinct with our class. And frankly, underneath, it's pretty much the same. So Kotlin will just generate a getter for us. It's going to generate our field. And the assignment for the field is going to be inside the constructor. So the init here is the constructor. There's no real keyword for it, but the bytecode has to have a way of distinguishing constructors from just the regular methods. But if you don't want to have the getter, you can annotate the properties of the actual class itself with the JVM field, and this will allow you to strip out the getters. So in Java, we could manually do this, but in Kotlin, we have to use the annotation to be able to achieve the same effect. And so we can see if we go into the bytecode that the getter is gone, and now we've just got the public field, which is, again, final. So null. So Kotlin enforces the ability to declare something as being nullable or not. And the way in which this kind of works underneath is when you run the compiler, it's going to check for anything which is not nullable that you're not trying to invoke on it. But the compiler is a bit of a pessimist. It doesn't actually trust you. So it will still check at runtime whether or not the variable you have passed it is actually truly not null. And if you don't declare it as being null, it knows that the bytecode it's going to generate will always have that null check. So in both the source code and the bytecode, there are a few compromises, but for the most part, Kotlin is doing pretty much the best to ensure that you don't have the nulls where you don't expect them to appear, and that they do appear where you do expect them to be. The next thing is extension functions. Extension functions are really, really helpful, and that it allows us to add methods to classes that we don't really control, or classes which are closed and we can't actually extend them. And the way in which this works is it just generates a static function, and the static function is just going to take the type and make that the first parameter in the argument. So we can see here that the first parameter is our context type, and then we're taking the integer as the next one. Again, Kotlin will check to see if it's not null, and then invoke the static function that we're trying to wrap here. So effectively, you can think of the type gets replaced for the first parameter in the function. Okay, so inline functions. So with the inline function, the whole idea is that we don't actually want to have a static function. We want to inline all the code. And the way in which this works is Kotlin will actually generate, sorry. I deleted a slide. Oh, sorry, yeah, this is the slide. Sorry for that. So Kotlin will generate this function, which I've mostly grayed out, where you're actually passing in an object as the argument. But in fact, if we actually invoke it, we can see in the bytecode that it's not actually invoking this function. It's just inlining everything into where we're actually calling it from. So some of the things that we get with Kotlin is, so Kotlin will have a bunch of things that look like extension functions, but what it's actually doing is it's so in the collections we have map, filter, and sum, and a few other kind of helpful functions. So if we have a nice little topic fragment here, where we've just got a function that takes a number and then multiplies it by 2, and then we're going to map that over our array. What it actually generates is all this, but that's a bit hard to read, so here's it in Java. And the first thing you'll notice is that the array collection is actually using a class. And so we're boxing our numbers. But the for loop is pretty much similar. It is pretty much what you would expect if you're iterating over a collection and building up a new variant of it. So one of the things you have to remember when you're dealing with the primitive collections is to use the primitive factory functions, because if you use the array of or array list of, you will get the box variants. So this fixes our bytecode so that we've now got the primitive integer, and our for loop is a little bit simpler and easy to read. So for the most part, the for loop is the map and filter and all that are going to always compile out to either a for loop or a while loop. So who knows what will happen if we actually chain these functions together? Has anyone actually kind of had a look underneath? Well, if you actually get into the bytecode, for every function that we have, it's going to add another loop. So if you have a quite large collection and you're chaining about 3 or 4 functions, it's going to iterate over that entire collection 3 or 4 times. Now, we can squash all these functions together using something called a sequence. But one of the problems with the sequence is that we can't inline the functions that we were using before with our method references. So if we actually dig into the bytecode, we'll find that we're generating anonymous in a class to pass as a reference, because the sequence is expecting to get an object which it can invoke. And because there's no way for us to kind of really have, in the runtime, especially on Android, pass these method references down, Kotlin has to generate a class which then internally is going to be using reflection. So if you're going to be using method references, be very careful about it. In fact, I would say probably you're better off just using the Lambda syntax pretty much everywhere inside your code base. And then at the end we can call toList, and this will just iterate over the entire collection once and actually invoke it out. Now, I don't have the bytecode for this because digging into the sequence is quite big, so we can see that we create the sequence, and when we're using the lambdas, it's actually going to recycle a lambda, so the lambdas are actually held in a static context. So because they're not context capturing, it's going to be able to recycle them between invocations. Right. Okay, so data classes. So data classes are a nice thing that we have in Kotlin, where if we need to have something which has the equals and hash code, Kotlin will generate these for us. And these aren't particularly too exciting, but one of the things I would like to kind of dig into is things like the destructuring. And the way the destructuring actually works in Kotlin is it will actually generate for us these component methods, and the component methods are defined in the order in which we're inserting the parameters into the constructor. So the first parameter will be the description here, and the second parameter will be the talks. And when we destructure, When we destructure it, it's just going to, on the left-hand side of that tuple that we have here, it's just going to, on the right-hand side, call component 1, then component 2, then component 3, then component 4, then component 5. So if you want to destructure something, you want to get the first and, like, say, the fifth element of an object, the destructuring isn't really going to work. And if you get the names on the left-hand side, if you name things differently, Kotlin will complain and give you warnings. So the next thing is the copy constructor. So with data classes, if you want to be able to, you can use them in a very immutable way, so that every time you have a change in, say, like a stream of events, you can use the copy constructor to return a new variant of the object. But we can see that it forces us to have not null. But that's a bit of a problem because we can just pass in a single actual argument to the copy constructor. So how is it that Kotlin is able to pass in all the arguments when we're actually only ever giving it one? And this is where the default copy constructor comes from. So reading if statements in bytecode is a bit of a pain, so I'm going to convert this one back to Java as well. And we can see that we're taking a speaker as a var0, that's the object that we're trying to copy from, and then we're taking the arguments of the constructor. The second last argument is just this integer, and the integer is actually a hash code, which is just a single int, which Kotlin then calculates to understand which arguments that we want to pass in. So if we only want to pass in the description here, Kotlin will generate the hash of 6, because the hash of 6 is the only one which doesn't meet the condition where we want to copy the variable from the object that we're trying to clone. I don't know what the fifth object does. I haven't worked that out yet. All right, so lambdas. So there's a few different ways in which Kotlin will generate lambdas. So if you generate a lambda for a SAM, it's not quite the same as a context capturing, and it's a little bit different to how you would have a non-context capturing lambda. So let's just take the canonical on-click listener for a view. And so what Kotlin's going to do behind the scenes is just generate the anonymous class, which will then implement the interface for us. But we can see that it's also got this instance feel to it. And so Kotlin knows that our SAM method here is non-context capturing. So it knows that it can actually recycle that call handler between instances of the class. So if this is a view handler for a fragment, it won't recreate that lambda even between device reconfigurations. So as long as your process doesn't die, you can recycle these lambdas between instances of the class. So the next thing is just like a regular lambda. So I use these a little bit in the Kotlin code, just for being able to have a nice method that I can pass around. But remember that we still have to compile these down to anonymous classes. And again, Kotlin will generate us a nice static instance that we can recycle between instances. And because of the way generics work in Java, or the JVM, sorry, everything returns object. In fact, the compilers for both Java and Kotlin will actually just put comments in the bytecode so the compiler knows what to cast the object back to once it gets something out of the function. So if we go look inside the Lambda, we can see that we're extending from the Lambda class, which is implementing function 0, which is going to just return nothing. I think there's about function 9, but if you're passing 9 arguments, you should be probably passing an object instead. And so we've just got a regular constructor and our static constructor, which is going to be used to initialize our instance, which is going to be recycled between things. Now, with the static constructors in the JVM, these are invoked as soon as the class is referenced. So if you're somehow putting something very complex in these things, remember that this will be invoked automatically as soon as the class comes into scope. And if we go look at the invoke function, we can see that we've got the synthetic invoke, which returns the object. This is just because of the way generics work in the JVM. And then we have our actual implementation, which is going to return the type that we've typed the lambda for. In this case, we're just returning a string that says, I am a lambda. Now, this means that a regular Kotlin function is going to have about 4 methods. So if you want to bring your method count down a bit, maybe consider making some interfaces and then have your functions implement those SAM interfaces. Now, if Kotlin is generating these static instances of Lambdas, what happens when we context capture something from a non-static context? So in this case, that's just the invoke. Sorry, yeah, okay, getting ahead of myself. So in this case, we've got a speaker, and we want to get the name of them out of the speaker inside the Lambda. So one of the things that we can see is that the Lambda is going to invoke this static accessor method and then pass in an instance that it's captured of the enclosing class. So we're calling the accessor getSpeaker $P on the actual LMBD class. And so if we go back to LMDB in the bytecode, we can see that we've got this synthetic accessor method. And this is because Lambdas and anonymous inner classes and inner classes can't be nested. So in bytecode, there is no concept of nesting. So if you want to have inner classes accessing private members, both the Java and Kotlin compilers will have to generate these synthetic accesses to give the inner classes the ability to actually call these internal fields. And the way we can get rid of this is, again, with our friend the JVM field, and we can mark the scope as being protected. Now, Kotlin will complain about this because a protected scope in a final class, which Kotlin by default is making all our classes final, is effectively private. And this is true, but we still need our inner classes to be able to access things. So if you want to get rid of the warning, we can just suppress it. And this is important because in the second last release of Kotlin, there's an option to turn warnings into errors. And I would encourage everyone to turn all your warnings into errors because the Kotlin compiler will give you warnings which I personally think really should actually be errors, but it's a bit like me. Like that. So now if we go back to our Lambda in our invoke function, we can see that we're just getting the field and then just invoking the object directly. So we don't actually have to have that synthetic method anymore. All right, so files, values, and functions. So one of the things that we can do in Kotlin that was just not possible in Java is have just values and functions declared in a file without any kind of class. So if we just open up a file and put like a speaker object in here, what happens underneath is that Kotlin is just going to generate a class for us, and it's going to take the file name and then just append KT at the end. Now, all functions and values in a file are all static by default. So we can see here that we're just going to put our static object into our file class that's been generated for us. So our functions are static, our values are static, but if you don't put a const on your value, it will actually assign the constant twice. It will assign it in line, and then it will assign it again inside your static constructor. So again, if we put the const in, this disappears, and then we just get the single assignment in line. So objects is the other way in which we can do statics. So if we go and open up the object, we can see that we have this public static object instance, which is initialized from our static constructor. But objects by default aren't static. The values and functions they hold are actually bound to the instance of the object. So everything is bound to instance rather than being a static context. So if we declare a value, again, we run into that same problem where the static constructor will align it. So even though we've declared a public value in our object, because we haven't marked it as a const, it's going to generate the getter for us because all the values in our objects are not static by default. So again, if we make it a const, it will create our constant public final here. Functions will just be attached to the instance rather than being static. If you do want your functions to be static, you can use the @JVM static annotation, and that will give us a static variant of the function. So instead of having to get the instance first and then just do a virtual invoke, it will just do a static invoke instead. Who's using companion objects? One person. Okay, either everyone has seen my talk already, or I'm not doing Kotlin correctly. So if we declare a companion object in a fragment, often we'll need companion objects to hold the statics for us, because we can't declare a static inside the class. So if we look inside our topic fragment, if we look inside our static constructor, because the companion object will use a static instance, so we need a static constructor to invoke it, we can see that the companion object is being invoked at this default construction marker, and this is because the constructor for our companion object is actually private. So we need to generate a synthetic object to be able to invoke the default constructor marker. Now, the default constructor marker is marked package final, so the bytecode doesn't really care about package scope. The package scope is really something that only kind of exists inside the languages. The bytecode can often get around it a little bit more. So we can actually pass in a null, whereas if you were able to invoke this in the source code, you wouldn't be able to pass in anything to be able to satisfy it. So that's how it prevents you from creating the companion object multiple times. Now, if we put a val without a const in our companion object, we get some really weird behavior. And to show what's happening here, I'm just going to invoke it inside the constructor for the topic fragment. And so we can see, even though we declared a public value string, it's going to give us a private static string instead. And so we can see inside our static constructor that we're going to assign the value again twice, even though we can be inlined. And inside the constructor for our topic fragment, where we're trying to get the value, it's actually calling a getter on the companion object. So if we go inside the companion object, we can see that the companion object is now invoking a synthetic accessor on the topic fragment to get the thing which we declared inside the companion object. And so the topic fragment is just going to return the companion object. Now I tried to graph this out, and this is what I came up with. It's like utterly bizarre, and just a lot of time you don't expect this to happen. So it's generating a bunch of methods that you just wouldn't expect to be there. And again, the way to get rid of this is to make it a const. In fact, I would say don't put anything in the companion object unless you can make it a const or a function that uses the const that you've put inside the companion object. Don't put anything which is not actually able to be a function or a constant. And so now we can see that we've got a public final static. So if we make something private inside a companion object, we'll get the private static inside the topic fragment, as well as Kotlin, because we've made it a const, will just inline the access inside the companion object. So again, even though the companion object will compile out to another class, because they're constant variables, Kotlin knows they can just inline them wherever they've been invoked. Unless you think that I just made up some really trivial thing, I went through the DroidKaigi app and found an example of where we're getting these that crazy kind of cross-calling thing. So in this case, we've got this private formatter, and we can't make it a constant because it's a class. The fun parse date string, that's probably fine. But one way in which we could get rid of that kind of craziness in terms of things calling each other is to actually declare a private object in the same file. Now, private classes in Kotlin are file accessible, but in the bytecode, what it actually does is it generates a package private class. So if you want to have package private variables that you want access in a few classes in a single file, declaring a private object is probably the best way to get around that. And yeah, so if you want private consts, they're fine. I probably wouldn't put anything more than maybe a factory function for fragments in a companion object. You're probably better off using just an object or extension functions to be able to add static functions to your objects. So the next thing is, just on the same topic of scope, is if we look at the Lambdas in this example I've got from the DroidKaigi app, we can see that we're getting synthetic accesses. And this is because lazy is implemented using anonymous inner classes. And so, again, if we want to be able to get rid of these synthetic accesses, we can mark the fields as JVM protected. Sorry, JVM field protected. But if we have a few parameters to our class, this becomes a little annoying, and I don't really want to have to add suppress warning on every single line. But we can actually just suppress the warnings on the entire constructor itself, and this will allow us to get the protected fields that we need for our lambdas. And that's about it for me. So this only kind of really scratches the surface. There's a lot of kind of weird things you can do, and there's a lot of ways in which you can get the Kotlin to generate bytecode, which is more optimized. But for the most part, I think probably the most important things to take away is make everything you can a const. Be very careful with using method references. You're often probably better off just using the Lambda syntax. Method references can be inlined, but you have to make sure that you're using them in a place where you don't have to pass a reference, because Kotlin won't generate a cheap, efficient reference that you can pass around. I also record pretty much most of the Sydney tech meetups, so if you want to go see some videos online, go to YouTube ANZ Coders. I work for Moneytree in Sydney, but we are based here in Tokyo, so come talk to me afterwards about that if you're interested. And yeah, thank you. Questions?
Thank you for a great presentation.